A body is dropped from 300 feet with an initial upward velocity of 30 feet per second. Since there's no air resistance, the only force acting is gravity, with an acceleration of g equals 32 feet per square second downward. That gives us the equation, dv dt equals minus 32 integrating both sides with respect to time. v, t, equals minus 32t plus c. At t equals 0, velocity versus 0 is 30 feet per second, so c equals 30. Therefore, the velocity at any time t is v, t, equals minus 32t plus 30.
T equals negative 16t squared minus 30t plus another constant, c2. At time t equals 0, the height is 300 feet, so s of 0 equals 300. That gives us c2 equals 300. Hence, the position function is s of t equals 300 minus 30t minus 16t squared. To find when the body hits the ground, we set s of t equals 0. That gives the quadratic equation, 16t squared plus 30t minus 300 equals 0. Solving this equation by quadratic equation we get approximately 3.49 seconds.
A. How air resistance, altitude, or object shape might affect the motion. Air resistance opposes motion and increases with velocity, reducing net acceleration below g equals 32 feet per second, shortening fall time and
Then, we continue with the question how the differential equation would change if air resistance proportional to velocity. In the ideal case, there is no air resistance, so the velocity will increase with time as the equation will write in Vt equals to V0 plus Gt. The object will keep speeding up until it hits the ground. But in reality, the air resistance will push against the motion. When drag is proportional to velocity, the equation will become m dv dt equals to mg minus kv. As the object speeds up, the drag will increase and it will slow down the accelerations. Eventually, it reaches a constant speed called terminal velocity where Vt equals to mg per k. If drag is proportional to velocity squared, the terminal velocity will become Vt equals to square root of mg per k. So, the air resistance will make acceleration non-constant and the object no longer speed up forever. Lastly, let's look about the last question, which is why understanding this effect is important in engineering, aerodynamics, or space exploration. In engineering, it helps design paraculars, elevator brakes, and safety systems like airbags and drop towers, which can ensuring smooth deceleration and preventing accidents. Moreover, in aerodynamics, it used to predict how aircraft, missiles, or even sport balls move through air, which the accurate drag models will help to improve the fuel efficiency, range, and stability. Furthermore, in space explorations, it's crucial for safe re-entry of spacecraft like Apollo or SpaceX capture, which can correct drag control, which prevent overheating or hard landing. Therefore, it can also allowing a safe return to Earth. So, in conclusion, understanding this effect will allow engineers to design a safer and more efficient system in many fields.
This experiment analyzed the motion of a body dropped from a height of 300 feet with an initial velocity of 30 feet per second under the assumption of no air resistance. Using the kinematic and differential equations of motion, the velocity of the body was expressed as formula and answer like below.